Hi, welcome to the Math Center. I'm Roy Menon. Today we want to talk about an idea using integration. So the topic, using integration to find arc length. So let's start slowly. Yeah? Let's say we have a curve, and the equation of the curve is given in Cartesian form. So let's say we have y equals to fx. Now we want to find the length of the curve from, let's say, P to Q. Okay, this is the length we want to find. So let me just do a wriggly line a little bit so that you know exactly what we're trying to find. Okay, so this is what we want to find. Okay, we want to find the length of that arc. Now what we'll do is we will say the coordinates of P, let's call it x, fx. Now let Q, the coordinates of Q be x plus delta x, and the y coordinate will be, okay. When you see notation like this, it is implied that Q is very near P. Okay, Q is a point that is near P. Remember, we are trying to find the length of this arc. Okay, now because we have said that, let me write that here. Okay, Q is very near P. So let's call the length of, okay, the length of PQ, let's call it delta S. Okay, the length of PQ is delta S. Now what we'll do is, because Q is very near P, we will approximate this by drawing a line joining P and Q. Okay, again, because Q is very near P, we will just say, why don't we just go ahead and approximate this length by drawing a straight line connecting P and Q. Okay, this line PQ that I've drawn here, this straight line, some books call it a chord, some books call it a secant line. Okay, sometimes we like to reserve the word chord for circles, but whatever, yeah, we'll just call PQ a straight line. So now what we can do is, we know this distance and this distance. Okay, this one here will be delta x, and this one here will be delta y. Okay, now there is no problem there, because delta y will just be the difference in the y's. Okay, so if I have fx plus delta x minus f of x will give you the change in y, and we'll call it delta y. Good. So now remember, this is what we want. We are saying that this is about equals to PQ, so I'm going to say that delta S squared is approximately equals to delta x squared plus delta y squared. Now where do I get this from? Pythagoras theorem. Okay, so again let me tell you, this is what I want, the arc length, but I'm saying that Q is very near P, so let me just go ahead and approximate that by a straight line. And using Pythagoras theorem, I'll say that this delta x squared, okay, delta s squared is approximately equals to delta x whole thing squared plus delta y whole thing squared. Now, I'm just going to call this delta x squared and delta y squared and delta s squared. Now what do? Let's divide throughout by delta x squared. So when you do that, this is what you will get. Let me maintain my approximately equals to. Okay, so what have I done? I've divided throughout by delta x squared. Okay, so when you do that, okay, note this thing here becomes 1. Now let me continue on this side. What are we going to do? We are going to let delta x tend to 0. Okay, I want to remind you, right, very important idea about delta x. This delta x is something that is something in calculus we consider it measurable, yeah? As opposed to dx. Dx is something that is very infinitesimal. So let delta x tend to 0. When you do that, what happens is delta s delta x becomes ds dx, and delta y delta x becomes dy dx. Okay, so now I'm going to write what I have here using the d's. Okay, now this is an important idea. Let me just continue here. So I'm going to write ds dx whole thing squared will be equals to, now this is 1, so we don't have to worry about it, 1 plus dy dx whole thing squared. Okay, so now we can take the square root. Let me write it here. Okay, ds dx will be equals to the square root of 1 plus dy dx whole thing squared. Okay, now what we can do is we can bring the dx up, so it will become ds equals the square root of 1 plus dy dx whole thing squared, and we have a dx here. What have I done? I've brought this dx up. Okay, now we have a ds on the left. Okay, we have a ds on the left and we have a dx on the right. The natural thing to do would be to introduce our symbols of integration. But this ds, when you add all the infinitesimal ds's, we are going to get the arc length. And now we can write the square root 1 plus dy dx whole thing squared dx, and let's say x goes from x1 to x equals to x2. Now this is how they derive the formula for arc length when the equation of the curve is given in Cartesian form. Okay, very powerful formula. Now, one way for you to remember this, because some of you may even do engineering maths and you'll come across this again. So one way you can remember this is by thinking of ds squared equals dx squared plus dy squared. Okay, think of it along these lines. Okay, along these lines, and then what you do, you divide throughout by dx squared, and then you'll end up with the formula that we need. The reason I'm talking about this is because this is pretty straightforward. We only have we are given a Cartesian equation, so it's pretty easy. Sometimes in your exam, it may be your equation may be expressed in parametric form. So let's deal with that. Okay, let's do that. It only take us a minute or so to derive that formula. So I would think a convenient point would be ds squared equals dx squared plus dy squared. So now if we deal with parametric equations, okay, parametric equations, that means x and y are given in terms of a third variable. So let's just write x equals to f of t, and let's say y equals to g of t. So now from x equals to f of t and y equals to g of t, you're going to get what? Dx dt, dy dt. Yeah. So let's divide throughout by dt squared. Okay. So that's why I said this one here is a very important idea, and it's quite easy to remember. So divide throughout by dt squared. So I have ds squared. Let me do that. Dt squared equals dx squared over dt squared plus dy squared over dt squared. So now we can write down another formula for the arc length if the equation of the curve is given in parametric form. So now we have ds dt. Let me clean this up. I have dx dt whole thing squared plus dy dt whole thing squared. Okay? Take the square root. Ds dt will be equals to dx dt whole thing squared plus dy dt whole thing squared. Okay? So you want to find the arc length, we need to bring the dt up. So let me write it here. Okay? Let me write it here. So we can write ds equals the square root dx dt squared plus dy dt squared and dt. Now we have to introduce our integral symbols. Okay? On the left hand side, when you integrate ds, you're going to get s. So that's the arc length that we want. Okay? So we have the integral of dx dt squared plus dy dt squared and dt. Careful, these are values of t. So t equals to t1, t equals to t2. So if your curve, if the equation is given in parametric form, and if you're asked to find an arc length, this is the formula that we will use.